Okay, great. Thanks. This is the first one after the break. So thanks for everyone making it. I'm delighted to sort of have Lisa Manning here. She is the William R. Kennan Jr. Professor of Physics. The junior is with the William at Syracuse University. And she works on behavior of glassy materials and in context of biological tissues, looking at mode of emergent properties in them through that lens. She has had many honors, NSF Career Award, Sloan Fellow, most recently, Maria Gompert Mayer Award presented by APS. If I'm missing something. But well, that said, we're really excited about the science she's going to talk about. Off to Lisa.
Thank you. Thanks so much for being here. Nice to see all of you. Before I get started, I want to be sure to say that I would love to be interrupted with questions. My understanding is this is a broad swath of physicists from all the different places. And I'm talking a little bit, actually much about biophysics today. So if I say something and you don't understand it, you're doing everyone else a favor by asking about it, because somebody else probably has the same question. And the other thing I want to do before I get too far, let me make sure I can use this pointer. I checked it before. Yes, is highlight the people who did the work. This is my current group, so I'll talk about work by Kelly and Tyler. I'll also talk about some fantastic work by former postdocs, Ojan, Varda, and Sajjad in my group. Some of this work was in collaboration with Chris Santangelo and Andrea Liu, and Indrajit Ta while he was a postdoc with Andrea. And I'll try to highlight where people did the work as the talk goes along. So I'm going to start the talk by saying something very provocative. Actually, I didn't say it. The New York Times says it, which is the areas of physics by difficulty. This is a physics department, right? Look over here. Sand is the hardest. It was in print. OK, so why is understanding the mechanics of sand hard? And I think the idea is, I guess this pointer only works. Oh, I have to point at it. It's difficult to predict how sand behaves. And even in an idealized setting in the lab, so even a thing like this where each individual sand grain is exactly identical to every other sand grain, they're smooth, they're like perfect spheres, you know their elasticity. This is force chains in the material, and it's crazy. And you know this intuitively if you've ever been to a beach, because you can pick up sand at the beach and it flows through your fingers. If you compress it a little more, it flows a little less, or if it's wet, it does something crazy. And it also supports your weight. You can walk across sand at the beach, so that seems a lot like a solid. So this is a crazy material that changes its properties dramatically depending on its environment. And I would say, just to get us started, that the difficulty of the problem is not in the grains of sand themselves. We understand everything about the grain of sand, in this case at least. The difficulty is in understanding the emergent interactions, self-organized interactions between them. And that's what I'm going to refer to as emergent behavior for the rest of the talk when I talk about trying to predict emergent behavior. OK, and so why is it not working? OK, so Phil, physics colloquium. I'm going to give a quote by Phil Anderson. He has lots of good quotes. This is one of my favorites. He says, "We are so accustomed to the rigidity of solid bodies, the idea, for instance, that when we move one end of a ruler, the other end moves the same amount, that we don't accept its almost miraculous nature, that it is an emergent property not contained in the simple laws of physics, although it's a consequence of them." And so many of you have probably taken like a solid state physics class. You're like, oh, I know Ashcroft and Merman or whatever. I know how to compute when a thing is solid and maybe even its vibrational modes. I know. But there's many materials around us, like sand being one, that aren't crystals, and they still act rigid sometimes. And so Phil Anderson also followed up that quote with this quote, which is that the deepest and most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and the glass transition. And I think more generally I'm going to interpret what he means there. Things that are disordered don't have an a priori reason to be rigid. There's a broken translational invariance in crystalline solids, but it's not broken in disordered materials, and yet they still become rigid. So what's up? OK, that's the question. And I would say, OK, now we want to do something even harder. We want to not only take this material, which I will show you in a minute, looks a lot like a glassy granular material, which is the material that makes all of us up. It's groups of cells, or the material that makes up the zebrafish that I'm about to show you. And we want to not only understand its material properties, but we want to actually force it to in a particular shape in a particular time. Okay, so the bigger picture question is, well, how do you take a blob of this difficult material and how do I turn it into something that's the shape of a fish? That's a morphodynamics problem. Okay, so here's a picture of how the fish does it. So this is an egg yolk, and these are the cells that are going to become the fish. And you can see there's this stage called the shield stage, and then there's this beautiful flow, wait for it, right here, whoosh, down the sides of the embryo, and that's the long axis of the embryo, and you can see it's forming the nodal cord here and the spinal cord, and this is its face and this is its tail. So clearly fish managed to do that. Also, we managed to do it via a very not dissimilar process. Okay, but we can do it a different way. A glass blower can do this too, a skilled one, right? So how does a skilled glass blower do that? They start with a blob, a glassy blob of material, and they end up with something that looks like the shape of a fish. And I would articulate that there are two key ingredients that you need to be a glass blower and make this whole thing work. And I'll point out that biology does it without the external processor, without the glass blower. But if you have a glass blower, you can program stuff a little better. And the way the glass blower does it is via a mandrel rod or a special table that applies localized shear forces, basically pressure, shear forces, or whatnot. And they also do it by heat. And the reason heat works for glass is because glass has a fluid-solid transition. And so what you do is, if you want to stretch a particular part of the material, you first heat it up and it melts because that's what glass does. And then you stretch it in that area because you basically turned it into a viscous fluid. And then when you want it to solidify and you want to embellish, you turn the heat off and then it turns back into a solid, and you've set in place a reference state that you like that's useful for further elaboration. Okay? And I would argue, actually, there's evolving evidence in scientific literature that something like these two things are occurring in the zebrafish too. That's how a zebrafish works. It does these two things. And I'll go through that. And I have two parts to this talk, a part one and a part two. And I'll probably get through part one, and I probably won't really get to part two. But I wanted to tell you that sort of part one is, well, how do these biological systems go through rigidity transitions without having like the external glass blower to decide, here's how you should do it. You know what I mean? And then I think even more interestingly, but possibly more difficult, is how do you program specific localized forces that, oh, I want a flow inward, an invagination flow here, and I want this particular shape of a shear flow here in order to generate the shape of a fish, right? So this is the big picture question. And of course, I also think of myself sometimes as a material scientist. How could we make man-made objects that have these properties, right? Because that would be really a step forward in the type of things that we could build and the ways that we could manufacture things. So I'm interested in it from a material design perspective too. Okay, so part one, how does the system program its interactions to go through a rigidity transition? Phil Anderson told you this was a hard problem, so you believe Phil Anderson. He's right about these sorts of things. I would say that one of the things I need to tell you is that there's really good biology experimental evidence in the past 5 years, basically, that biological tissues are going through rigidity transitions. I'm not going to talk through these two references in detail, but if you're interested, you can go read them. They're gorgeous. And they basically say during two different developmental stages in the zebrafish decides to fluidize itself in a certain region, and that allows large-scale shear flows to happen. Okay, cool. I also wanted to tell you that I'm talking mostly today about what are called cellularized tissues, which are tissues that are composed of cells interacting with other cells. But a lot of our body is actually made up of extracellular matrix, and a lot of materials we're interested in designing are also like fiber network materials. And it turns out that fiber network materials also have a floppy to rigid transition. And I'm going to argue that in some cases, the origin of the two is the same physics. I'll tell you about that later. But here's the key idea. I have a network. It is what's called undercoordinated, and I will tell you what that means in like 5 minutes. But it means that there's sort of these branches that only have a low number of branches, 3 or 4 branches in the system. So the number of branches at connection points is called this connectivity. It's how many connections I have. The cool thing about these materials, you may have heard about them, they're extremely strain stiffening. What it means is they take a chunk of this material and it's really floppy to begin with. And then if I just change the size of the box, sometimes not by that much, all of a sudden it rigidifies by orders of magnitude. It gets a lot stiffer just by a change to the geometry of the box. And so this has been something that people have been interested in. So that's this axis, and you can rigidify the system that way. Or if I add more connections, I can rigidify the system. And we'd like to understand that because these are disordered systems again. How does that work? How could we design them? All right. So I and others, tons of people over the past 10 years or so have thought about what are the mechanisms that can drive these rigidity transitions. And I'm going to talk about two of them. And this picture is a phase diagram. And so if you're looking into the page, all the gray stuff is rigid. And all the stuff that's white outside of it is fluid-like or floppy. And so I can change whether something is fluid-like or floppy. Okay, let me say it this way. If I handed you a cup of water and I told you the cup of water needs to become a solid, what would you do? Put it in the freezer. Great. So that's this axis, changing the fluctuations in the system. I can give it more kinetic energy. That will make it a fluid or a solid. Okay. What else? You're all physicists. You got at least one more answer. Pressure. Perfect. Right. When I say this to biologists, they're like, I am not here for it. But physicists know this, right? So I can change the pressure. I can change 1 over the density. That's this axis. And I'll tell you in a moment, there's a third way. And this is the way that me and my group have thought a lot about. And I'll tell you about it in more detail later. There's a third way to do it. Okay, but let's focus on this axis. So everyone understands this one, statistical physics. Let's talk for a minute about this one, because this one's kind of fun. 1 over the density. Okay, so what goes on with that one? Okay, our intuition for like sand, okay, is that if I want to make the material solid, I compress it. How does that work? Fundamentally, it works this way. So in the simplest model of friction, like perfect frictionless disks, nothing else going on, I can say, well, I have NP particles of sand in my jar, okay? And in D dimensions, we live in 3 dimensions, so D equals 3 for us. I have NP times D degrees of freedom in my whole system, because each sand particle can move up, down, left, right, back, forth. Yes? Okay. Then if I compress the system, they start to make contacts. The sand make contacts with one another, and they're repulsive. And so each contact introduces a constraint between those 2 particles that constrains their motion. So if I make Z be the number of contacts per particle at a given compression, then the total number of constraints is, well, it's the number of particles times the number of constraints per particle, and each bond is shared by 2 particles, so I have to divide by 2. Good. Okay, then I just set these 2 equal to each other. I'm like, the thing has to become rigid when the number of degrees of freedom equals the number of constraints. That tells you in 1 line of algebra that the system becomes rigid when Z equals 2D. This Z is called the isostatic number. It's the number of connections you need in a network to make something rigid. So that's why it works. At low densities, you have less than this number of contacts. You haven't made enough to keep the system stable. And at high densities, you do. Cool? Okay, cool. Okay, this is called constraint counting, as with many things in physics. It was invented by Maxwell, like a long time ago. Okay, great. Okay. It turns out that this exact argument, maybe not this exact argument, there's a little bit of elaboration on it, but basically this exact argument explains exactly these 2 behaviors. So these are data from tissues. If you look at this little picture, they're actually counting contacts and showing that the contacts change when the system becomes fluidized. It's super beautiful. Highly recommend, okay, this paper. Cells basically behave as squishy spheres, and these 2 model like sand. And they become rigid due to this thing. Cool. Okay. But there's a whole class of cell types that are called epithelial cell types. And in epithelia, cells are confluent. That means there's no gaps or overlaps between cells. They're space filling. They kind of look like polygons. I'll show you some pictures. What it means is I can't change the density or the number of contacts by compression. They just are filling all of space. The contact number is not going to change. I'm not going to change the connectivity of the network. So this thing can't change its rigidity via that mechanism. So what the heck is going on? All right, we need a different mechanism. Cool. And I'm interested in that mechanism. Okay, so let's talk about how to think about where that mechanism comes from. So let's do Maxwell's constraint counting, but slightly more carefully. So now I'm going to show you a picture of a square in 2D. So this is a two-dimensional system on a flat thing. So I have 4 vertices, and that means in 2D I have 2 times 4 equals 8 degrees of freedom. There are 4 bars in this linkage. Each one of those bars is like a contact that introduces a constraint. So there are 4 constraints. In 2D, I have 3 rigid body motions, which I don't care about. I want to throw those out, right? So what are those 3? Up, down, left, right, rotate. Those are 3 rigid body motions. So that tells me I should have 1 non-trivial floppy mode left, and I've shown it to you by the dashed line. This thing can shear. Cool? Okay, good. Okay, if I wanted to fix that, I just add 1 more bar. Then I have no non-trivial floppy modes left. Cool? Okay, good. Okay, I could have been stupid in how I put in the extra bars. So let me show you that. So here's 2 plaquettes, and if I was smart about where I put the bars, that thing is still rigid. But I could have been stupid about where I put the bars, and I could have put them both in the same plaquette, and then I still have a floppy part. So you have to adjust Maxwell's constraint counting a little bit to say, okay, each time, and this is a fact, and I won't go into the details in this colloquium, but it's a math fact, that every time I have an extra constraint beyond what is necessary, I have what's called a state of self-stress. That's a state of tensions on all the bars that don't change the position of any of the nodes. And I've drawn it in here. There's a state of tensions, and that automatically comes along whenever I have an extra constraint. So therefore, if I have some extra constraints, I'll call that number m, then I have to subtract off these number of states in self-stress to really tell how many floppy modes there are in my system. Cool. There's a slight extension, okay? Slight extension of Maxwell constraint counting, mostly described by Caladay. Okay, but now I want to point out that there is a whole class of materials that don't even obey this extension. This extension is still wrong. Okay, so let's talk about why it's still wrong. Okay, here is a spring network, kind of like those fiber networks I told you we were interested in for all sorts of reasons, and I want to explain strength stiffening in that system. Okay. You can really well model these systems by a stupid energy functional. This is a stupid energy functional. This is the mechanical energy of that network. It's just the sum of a spring times the distance of the spring from its rest length squared. From first year physics, whatever you all are okay with this for each individual spring, and then I connect them all up together and everything is good. Okay. So in the diagram, there's the actual length of the spring, which is this capital L, and then there's the rest length of the spring, which is this little l. Okay, it turns out that in biological tissues and also in these collagen networks, the network coordination is almost always less than this critical value, which is 2D, which means that constraint counting tells you these networks should be floppy all the time. Okay, but I think you already have an intuition for this. If I took a floppy thing and I stretched the box, right? I stretched the box. At some point, so in this picture, this is the rest length of the springs. Basically, the cells are all happy. They can be their rest length. But as I stretch the box, basically, the springs can't be at their rest length anymore. They have to be bigger than their rest length because they stretched the box too much. So that means each one of these springs has an energy, which means it can't be at 0 energy anymore, and it's at finite energy, and somehow I made it rigid. Okay? The other thing I wanted to tell you is that, of course, if I, instead of envisioning that I had control over the box length, but instead if I was a biological system that had control over the rest length of the springs, let's say I could tune the rest length of the springs, increasing the size of the box is exactly equivalent mathematically to keeping the box size fixed and just shrinking the rest length. Exactly, mathematically exactly equivalent. Yes?
Box size. In this model, it's like is the boundary of the network.
Exactly. And if you want to, I'm not going to talk about it in this colloquium, but handling the boundary conditions in this system is challenging. So there's math to that. Okay. But anyway, yeah, we're assuming it's pegged to the edges. Okay. And so this is data from like real systems that this is the shear modulus, how stiff the collagen network is. And this is the applied deformation to the box. And notice that this is a logarithmic scale. So what you see is basically things start out kind of floppy depending, this is a change in particular concentration parameter. But the key thing is there's basically kind of a critical strain to the box at which these things jump by orders of magnitude. And this is, I said it was strain stiffening. Here's another picture of it. That's exactly what's happening here. Okay. I did want to show you that little thing. So for later, I think I want to point out that you can think of each length of each spring, each rest length of each spring, like how long that spring wants to be in its native state, is a parameter that in a biological system could be tuned maybe by a cell or a protein or something individually. And I will come back to that later, okay? But you could think about programming that. So as physicists, we normally think about changing materials by changing the pressure or the size of the box. But I'm telling you, there's an exactly equivalent thing that biology systems can do that's very cool and opens up a whole new set of possibilities that we should think about as physicists. Okay, cool. Good. Okay, so confluent tissues. I'm going to speed through this because I don't think it'll be very interesting to this audience. There is a class of models that people have used to model confluent biological tissues. They are well vetted. They work surprisingly well to explain the mechanics of these complex tissues. They're called vertex models. They basically assume that these cells that tile all of space like polygons are polygons, and that there's a mechanical energy associated with the shape of the polygon. That's how it works. So I'm not going to get into all of the details. Actually, I'll explain it to you as a physicist. So let's say each cell you think has a characteristic area that it would like to maintain. Let's call that A naught, a cross-sectional area somehow. It wants that, okay? And let's say it has independently a cross-sectional perimeter that it wants to maintain. And I have a tiling that looks something like this. Then as a physicist, the first thing you would say is that, all right, I should pay a quadratic penalty for excursions from that area and excursions from that perimeter. That's the first order term I should write down. That's this energy functional. To the students who were in the thing beforehand, this is what I meant by stupid model, right? This is kind of the dumbest model you could think to write down for this system, honestly. And I mean that in a good way. I think we should be working on simple models for things if they work. Okay. If you want to then, and maybe I should say a word, there's a ton of biology that supports this. There's like micropipette aspiration experiments by Evan. This has to do with cortical actin and myosin and cadherins and biology stuff. And for this audience, I'm not going to talk about it, but I would answer questions about how these things are actually regulated in cells if people care. Okay, good. The other thing about it is that this has units of length, this has units of area, so you can make a dimensionless parameter, which we call P0, which is the ratio of the perimeter of each cell to the square root of the area. It's a shape. So if I have a sort of rounded up shape, the perimeter to area ratio is small. And if I have an elongated shape, the perimeter to area ratio is large. Okay. And we have shown a long time ago now that, and we didn't understand it at the time when we found it, that this system has a fluid to solid transition as a function of this target shape index. So it was a complete surprise to us. We were doing numerical computer simulations of this thing. My postdoc, Max Dapeng B, who's a fantastic professor now at Northeastern, basically came back and was like, Lisa, this thing rigidifies. And I was like, no, that's wrong. We did something wrong in the numerics. But it does. It rigidifies at a characteristic value of P0, and that number is 3.81. Okay. Now we understand where it comes from. Basically, it comes from, well, before I say that, maybe I should say, cells can tune this variable. If I will tell you later that this is a key parameter. So if you want to take something, you want to take a confluent epithelial layer and you want to fluidize it so you can do convergent extension or something, or whatever, you want to solidify it so you can keep a fixed shape. Each cell can tune this P0 via expression of cadherins and via expression of actin, myosin, cortical molecules in order to tune this thing. So it is a tunable degree of freedom that cells can program. They have the capacity to do that. Okay. Okay. So what causes rigidity in these under constrained systems? There's a couple of review articles that we've written recently in case people actually want to like look at all the math of it. Here's the basic idea. So you remember this plaquette here? This is our familiar thing. I didn't say anything about its geometry. I only said about the number of things it had. But I could take these two edges here and I could stretch them out. There's no reason I can't do that. And you can see that if I stretch those two edges out, the other edges become more and more collinear. Does everybody see what that picture is saying? Okay. And then what happens, right, when they become collinear is that there's a floppy to rigid transition. Even though constraint counting tells me this thing should always be floppy, right? We already did that. This thing should always be floppy. But if I make the distance between D, between those two endpoints, if it's less than the rest lengths of all of those three springs, then it's floppy. Everything's happy. If it's exactly equal, it's critical. And if it's longer than that, you know it becomes rigid. This is how like guitar strings work and the whatnot, right? Like it becomes rigid. We know that. Okay, so why does it become rigid? We can say, well, it's not because of constraint counting. So it actually turns out that right when this thing becomes rigid, there's a state of self-stress that emerges. So it's even worse. I actually have 2 zero modes in my system, 2 floppy modes right when this thing becomes collinear, because I can measure that there's some tension in the string. Okay, so that means there's a state of self-stress. I've drawn the 2 linear zero modes, and you know immediately what went wrong if you look at a picture. Immediately what went wrong is that the obvious perturbation of that object is turns into a right triangle. And so I perturb the length of the string. You know, for a perfect right triangle, because of the geometry, the perturbation only happens to second order in the displacement. So before, it turns out, and I'm not going to go through all this math, but it turns out constraint counting is basically a rank nullity theorem on a linear perturbation. And now I'm telling you is you have to consider the second order perturbation to get the math right. Okay, that's the deal. Okay, mathematicians actually have known this for some time. People like applied mathematicians who work in this field, they know that there's some systems at which you have to think about second order perturbations. What we have done is basically trying to ask what do physicists care about? Like when we say something is rigid, what do we really want as physicists it to mean? I think what we really want it to mean is that it costs 0 energy. So something is floppy if I can move it at 0 energy cost. Okay, something is rigid if it costs finite energy to move. I think that's a valid thing. It turns out that the definitions that mathematicians usually use, which is called structurally rigid, is not the same as that. There's even some examples that you can cook up that do that. And so first order rigid is like a nested, so this is constraint counting. First order rigidity is constraint counting. What happens in these other the system of like a guitar string, it's second order rigidity, and that's a larger class. You can have an even larger class that's energetically rigid. There's a lot of math. I don't want to go through all the math here in this colloquium, but anyway, you can do this. And I would argue you have to start to ask questions like, what do I really mean by rigidity? And you have to be careful about it. So there's a lot of math here. Okay, the next thing I'll say is that you could ask, well, since I care about energetic rigidity, are vertex models energetically rigid? Because I showed you an example that was like a 3-bar linkage, which is like a very simple object. But like I'm talking about like n is a very large number of things. Does it always happen? So in this paper here, we prove, again, lots of math. Yes, it turns out that vertex models are second order rigid, and second order rigidity is what causes rigidity in those systems. It's the high N analog of what I showed you in the 3-bar linkage. Okay, and then I want to tell you a little bit more because some of you might find it interesting. It's related to some things that other people do in other branches of physics. So we wanted to know how easy is it for a system to find one of these rigidity transitions in configuration space? If I have this like generic disordered network, if it's a vertex model or a fiber spring network, how hard is it for the biological system to get back and basically do what the glassblower does and go back and forth across this transition? That's the question we'd like to ask. So I'm going to give you the answer, and then I'm going to give you a flavor of how we got the answer. So the answer is there is a manifold in the true differential geometry sense of critically rigid states. That means states just where the system is about to become rigid or has become rigid in the space of configurations of these high dimensional spring networks or vertex models. The manifold we can prove is codimension 1. It means that if your space is 3-dimensional, your manifold is 2-dimensional. It basically is 1 dimension less in the configuration space, which means you're very likely to run into it by generic dynamics. There's a lot of it, actually. Okay? The third thing you can prove is that there's a natural set of coordinates that parameterize this manifold, again, in the differential geometry sense. So you know like the first and second fundamental forms of the manifold, and you can actually do things on the manifold and search it. Okay, that's a little technical. I just want to give you, because some of you might enjoy it, a little flavor of the type of math in case it interests you, because I know some of you are thinking about research directions and things like that. So how do we do this? The first thing you need is you need basically to connect the vertices to the edges. And there's a matrix called an incidence matrix that does that. If any of you work on networks, you've seen this type of notation before. And then here's the boundary conditions that I'm not going to talk about at all, but you can include them in this situation and mathematically. So those are the vertex position. Those are the bonds and springs. There's a mapping between them that talks about the edges. The incidence matrix tells you which vertices are connected by edges. Good. Okay, and then there's boundary conditions. Okay, so now the thing that you want to do, it turns out, is you basically want to, the rigidity transition occurs when a configuration satisfies that the derivative of the energy with respect to these vertex positions is 0. That's when, I'm not going to go through exactly why, but it might be sort of obvious that that's a critical point for this rigidity transition. It's basically because there's exactly 0 stress in the system right there. Okay? Remember this 3-bar linkage I told you about that was springs? This is what that manifold looks like in configuration space. Let me see if it'll play. So that colored object with different colors, that complex object, is the critical manifold for this 3 things. It's horrible. Chris Santangelo actually worked this out before we started working together, actually. Okay, so it's very ugly. It's ugly. Okay, so what we did together is we said, can we de-uglify it? Can we make it less ugly? Okay, and the idea, I just want to tell you the idea of it, the flavor of it, is can we coarse grain the lowest level variables, which are these node positions, into higher geometric quantities, and generically we'll label those with H's. Okay, and the idea is then we can break down this partial derivative into a part that depends on, we're calling it a generalized stress. And then this is a geometric relationship which describes the geometry that relates nodes to edges, for example, or something like that. Okay, and there's a generalized stress, which is the derivative of the energy with respect to these H's that we're going to call a state of self-stress. Okay. Okay, and the question is, can we pick this H to make things not ugly? That's the game. The game is to pick H to make things not ugly. And the answer is yes, you can do it. So it turns out that this particular choice of H gives you a linear equation to solve, and therefore you can always solve it. And therefore, if you give me your network structure, your boundary conditions, and any geometric state of self-stress, I can find a vertex set of configurations that satisfy it. Which means that I basically have a mapping from this ugly space to a very, very simple space. And this, it turns out, is the natural set of coordinates for this manifold. And I can search on this manifold. So that's the math, in case anybody wants to talk more about the math. Okay, cool. All right. Oh, that was for central force networks, like spring networks. Kelly, who is a brave student in my group, has generalized this to vertex models. It can be done. It is horrid. We have spent the last year trying to do it. It can be done. It's actually surprisingly not so hard. And I mean, once you figure out the answer, then you realized it was easy. And then the other important result, though, is that for vertex models, the rigid states are also codimension 1 in the space of configurations. That was really important to us because it's mean that biological cells can, under generic dynamics, can tune themselves to a rigidity transition. That was very interesting to us. Okay. Okay, so now you saw the math between the results. This is the results, and this is the natural set of coordinates. Now I explained to you what the natural set of coordinates was. And we have some papers on this stuff. Okay. One more thing you can do with this, which I think is very interesting, is now that we've parameterized this this ugly manifold into a nice space, we can use gradient descent to traverse this space and solve really problems that would have been incredibly difficult. So let's say you told me, hey, Lisa, I have DNA basically struts that I can self-assemble. Could you make a critically rigid system out of struts of all the same length? Could you self-assemble one? Because then you would assemble a DNA system perfectly at the edge of one of this critical transition. So any perturbation would make it stiff or soft, and that might be a very useful mechanical property for a material. We can do that. And so we can, this is an optimization for equal length. So it turns out you can, actually, because the space is so big, you can find a solution where all of the edges are equal length. You cannot, in general, find one where all of them are equal tension, and that's interesting. Okay, but I won't explain why. You can make things that have the biggest bulk modulus possible. You can do all sorts of things. You can make ones that have the biggest shear modulus possible. And we're using this technology to like make, basically mechanical metamaterials that have these properties that they can go right back and forth across the rigidity transition and have other specific designer properties on them. So it's kind of neat. Okay, that math allowed us to do that. Okay. So that is basically what I wanted to say about rigidity transitions. So there's two kinds of rigidity transitions, first order and second order, and biology uses one or the other depending on what it needs. It turns out that second order is pretty cool for a lot of reasons and highly designable, and that might be interesting from an evolutionary standpoint, but I'll leave it there. Okay. The second question is that now that we understand the material properties, we have what's called a constitutive law for these materials. We understand how their material properties emerge and can be tuned. Now I want to drive this system to a specific shape. How do I put forces in a specific pattern in order to make the system flow in certain parts or not flow in certain parts or do what it needs to do? That's the last, I think I have about 10 minutes, about 10 minutes of this talk. Okay. So your physics department, you must have seen like 4 slides like this in the last 4 colloquia. How many times have you seen this slide? 2 or 3? Yeah, a large number of times. Okay, so everyone knows how this works, right? Machine learning, neural networks, the future of everything for all funding agencies especially. Anyway, okay. So the idea is there's always a cat and a dog. Those are some input. They're like a list of pixel, how intense the pixels are, right? It's a vector, okay? Then I've drawn one layer. It's usually a lot of layers. So you have all these hidden layers of interactions, and there are nodes that basically weights that go between these nodes. And the goal is during a training phase, you want to update these weights, these black arrows, these weights, so that this output nodes will say either cat or dog. They'll say cat when you see a cat, and they'll say dog when you see a dog. That's the idea. Okay, and you know that the way that everyone does this is that what happens is you send it forward through, and when you're during training, you send training sets through, and so you have an actual output, and you want the predicted output, right? You want cat, it should be a cat. It has a cat label, and you're like, how close did I get to cat? And then you update the node weights in order to make this cost function smaller. Right? And how do you do that? You do it via backpropagation, which is this lovely algorithm that allows you to do it in a layered network in a smart and efficient way. You can calculate that derivative in a smart and efficient way, right? Give me a thumbs up. Everybody's cool with this. This is how this works. Okay, good. Okay. So the new idea that's emerging in some places in our field is that, well, there's kind of a lot of systems that have a lot of internal degrees of freedom that if you squint your eyes, they kind of look like node weights in a neural network. They're individually tunable degrees of freedom that could potentially be adjusted on the fly, and maybe you could make a physical system compute something or accomplish a task if you knew how to do the training properly on the physical system. That's the idea. So here's some examples. This example is cool. It's basically they turned a vibrating plate into a digit recognition system. It's super cool. It did require an external processor. So they had an external processor that really did the backpropagation. It told them how to adjust those weight degrees of freedom in order to get the system to do this digit recognition. This one is super cool because it does not require an external processor. This is a set of variable resistors. So the tunable degrees of freedom is the variance on each resistor, but it tunes itself via a local rule, and it can also do digit recognition. This one did iris recognition, but flower, petal, sepal, whatever, you know that one too. But it did some recognition, but actually now it can do digits. And it's a small network. And then you can also have networks that sort of try to transmit mechanical information or do a couple of other sort of maybe things that are more specific to physical systems that you might be interested in. And that's this last example. For people who don't know, I would say that this is over the past 10 years, basically the people who have been working in neuroscience, because neurons are physical systems that have to physically interact, they've come up with some really cool algorithms that basically do back propagation, but on a physical network using local rules. So you might say, I don't know, because back propagation is an all-to-all thing. Like to compute the gradients you need to know all of the weights at the same time. In a physical network, you don't know all the weight. Like this node only knows about its connecting nodes. It doesn't know about all the other nodes. But it turns out there's some new algorithms. One is called equilibrium propagation. There's some contrastive learning. Anyway, the neuroscience community has told us basically how to do this, which is neat. Okay, so now we know how to do it. Okay, we know how to do it in a physical system. Okay, so there's tuning degrees of freedom and there's a task. Okay, so for the last 5 minutes, I'm going to show you our thoughts about turning, well, I don't want to turn a living developmental system into a general computer. Like that's not what I want to do. But I might expect that perhaps developmental systems have been optimized to have local rules that do the task physically, and so I don't have to go in with an external processor or correct them, they just do the thing I care about. And maybe I could use this framework to learn about it. Okay, so what are the inputs? There are the initial disordered cell positions and activity, which is sort of kind of varies from animal to animal. That's a disorder. There's also environmental cues. Then there's some rules that happen. In here, I'll talk about them. And basically what we want is a robust change to tissue morphology. Like I want it to flow this way, right? I want it to make this shape. Okay, so here the cost function is the actual state of tissue minus the desired state of the tissue. The tuning degrees of freedom are, in this case, these are epithelial tissues. And it turns out that basically folks have shown each one of the tensions on each one of these interfaces is individually tunable. Each cell can tune its tension via regulation of myosin and small GTPases for people who care about that stuff to do this, okay? And they minimize the cost function, maybe, question mark, via local learning rules on these adaptive degrees of freedom. Okay, cool. They're also a physical system, so they also have to minimize the physical energy at the same time. They're not allowed to violate the laws of physics. All right, good. Okay, so here's a picture of Drosophila. This is from Karen Keisha's lab. Look at that beautiful flow. And the flow I want you to see is this extensional one. There's also an invagination event, which we're going to ignore for now, although I'm interested in it. Okay, and here's a picture. Actually, this is, from a faculty member here at U Toronto a long time ago. But anyway, showing that this is the initial thing. And what I want you to see is this tissue, it turns out, has elongated to be basically twice its length. So you're looking at a side view, but it's extended like this. Okay, and so we want to understand that twice as long extension. It's like doubled its aspect ratio. So here we're proposing the task is to change its aspect ratio by a factor of 2. Cool. Okay. Oh, we do have a paper where we actually did the same thing, but we wanted to ask, how could a tissue fluidize itself? So I'm not going to talk about that today because I already talked about fluidity too much, but there is a way to sort of ask if I wanted to use this framework, could I make a tissue fluidize itself using the ideas I talked about previously? And the answer is yes, and it works really well. Okay, that's that paper. This is a new paper, which is saying, okay, let's say I wanted it not just to fluidize itself, but I wanted it to flow like this, and I wanted it to double its aspect ratio. Okay, the learning degrees of freedom that I have access to are these tensions on each interface, and I have a disordered system. And the cost function is just going to be, I have this length, I want to make it this length while preserving the area. I want a pure shear, and I want that. That's the thing. Let me just tell you, on a computer, if you have a model for the mechanics, you can basically say, well, how do I want to evolve the tension on each edge to minimize this cost function? That's back propagation, essentially. In an external processor, you can compute that. We computed it. Okay, we said, we're going to change the tensions to go downhill in this cost function the fastest way possible. And like, does it work? Like, if I just change the tensions according to this, does it work to generate convergent extension? And it does. So this is the optimal way if you want to. If this is your task, this is the optimal way to do it. So here's a picture. Yes, it works really well. So I'm just updating a model with these tensions computed by backpropagation to minimize that cost function. Okay, it works, good, okay? Then you can say, well, in the literature, they say that the local rule should be this. So basically what the literature says is actually the tension should be updated as the deviation of the angle from 90 degrees. So the tension should be higher when I'm more oriented in this direction. Okay, and so that's a second rule from the literature. So this is a local learning rule because it only depends, the tension depends only on the orientation of the object itself. That's it, right? Okay, so you do this and see if it can generate, does that local rule generate convergent extension? Yep, really, really well, very well. Almost as good as it turns out as the global gradient descent. Then I just told you there was this update in algorithm development, equilibrium propagation or contrastive learning. So basically what we did is we're like, hey, let's use the standard contrastive learning, physical learning, theory algorithm to write the best local learning rule from a theoretical perspective. Let's say I only had access to local information, but I wanted to soften the landscape. That's what it does in the right direction. So I basically am telling you that you can make up a new rule that just says that I want to minimize this using a local, I want to minimize the cost function using a local rule. Okay, and you come up with this. It's just math. You use the algorithm, it gives you this rule, which is a slightly different rule than the other ones. Okay, does it work? Yeah, it works really well. Okay, the last thing is that I could just shear the darn thing. That would also work to shear. So this is what it looks like if you just shear it externally. So now I'm saying like something else is happening and I'm just shearing the boundary. Okay, so the first thing to notice is that all of these rules generate convergent extension. They all work almost exactly as well as one another. And I think this is interesting because it is reminiscent of what over-parameterization does for AI systems. In other words, there's enough of these little tension degrees of freedom that the system is vastly over-parameterized for the features I want in this cost function. And that means there's a ton of good solutions. Like there's a lot of good ways to do this. Okay, but that's a little boring. Do you want to distinguish between these mechanisms? And here's the point. These all three do exactly the same amount of convergent extension, but they look really different doing that. These patterns of tensions are quite different. That's kind of interesting. Does one work best? Yes, the orange one works best. Okay, so this black thing is experimental data. This is the shape parameters. So the black data is experiments. The orange one matches it kind of remarkably well. That orange one, remember, we came to as a pure theory rule. It wasn't in the literature. We were like, oh, contrastive learning. What should the thing do if it wanted to do a local operation and minimize this cost function? That's kind of interesting. Okay, it also works for kind of, none of them work as well for this one. I wonder about the experimental data, actually. Anyway, we'll see. This is a much old, actually, I shouldn't say that because, yeah, Rodrigo is here, but he can tell me. But I think that this is a coarse-grained variable. And actually, we're trying to redo it now with better data, so we'll see what happens. Oh, I'm totally out of time. What I will say, too, is that, like, another thing that you get out of this approach is the orange. I told you the orange one works best. The orange rule works best out of the ones we tried. You could say, oh, is this system optimizing anything else? One thing that our colleagues, our biological colleagues said is, oh, these systems are trying to minimize the maximum tension on an interface. Having a big, big tension on a cell interface is not something a cell wants. But as you can see, the orange ones that match the data the best have the most tension out of all. They have a big heavy tail. So it does not seem that the system is optimizing that. It is seemingly optimizing whether a cut or a perturbation to an interface changes the whole structure. So I'm not going to go through the details, but there's a way of doing this with this mathematical framework. It turns out that this one is much more robust to mechanical perturbation. So maybe the system is optimizing that. We're not saying it is, but we're saying it's a candidate idea that somebody should now go and test. And then it's not doing that one. It's not doing that one. Okay, so I'm out of time. In summary, morphogenesis and shape-shifting require simultaneous control over localized applied forces and material properties. Biological tissues regulate these material properties via either first-order or second-order rigidity transitions. And we think that tissues can regulate forces without an external processor, and that physical learning algorithms might be a good way of figuring out how they're doing that. I'll stop there.
Can have some questions.
Thank you so much for the talk. So in the first kind of like GIF you showed where the zebrafish, like the cells actually move around, right?
Yes.
Would this kind of framework explain the cells moving around? Because from what you showed, it's just shape changing and like the tensions changing.
Yeah. Yeah. So the zebrafish example where it's called the shield stage and it moves down the sides, that system is actually much more well described by like a squishy sphere model. And although we haven't worked on it directly, we and a few others, I think that what's generating the direction or the signal for that migration is it's actually active cell migration along the ECM layer there. And the way that nobody's done any work on this, but like just to put it out there, I think one of the things that you could think about is whether because basically each cell, like in these tissue types, cells do have it depends on the cell type. Sometimes they have a propensity to break polarization and migrate in certain directions. And so you can also think about their migration direction as a tunable degree of freedom that they may have control over and that's influenced by external variables. And so you may be able to do something similar. Instead of treating tensions on interfaces as tunable degrees of freedom, direction or propensity for motion or motility migration direction as a tunable degree of freedom might work in that case.
Thank you so much.
Wait, so I was really interested by the physical learning algorithms that you had. So you created a differential equation, right, for the physical learning based off the local properties, right?
Yeah.
So local tension. So how exactly do you get that differential equation? I'm very curious.
Oh, yeah. Well, I can tell you very simply for this vertex model, the way Sajjad did it, it's very clever. Because I told you I wanted to know the derivative of the cost function with respect to the tensions.
Yeah.
That was the expression I needed to compute, right? So what he did is he changed the tensions and computed the change to the cost function, the inverse of that, which is super easy on a computer, and then you invert it. Very clever. That was Sajjad's idea.
Thank you for the talk. I wanted to ask, for the shape parameter that you introduced, where you take the ratio of the perimeter to the square root of the area, would that inform us how much energy needs to be expanded when a cell like tries to execute a cell process where it needs to fluidize itself?
Yes, in fact, people have, we have a new paper that's out on like one of the preprint servers where we actually can precisely quantify via some on like micro patterns, how much, what's the frequency with which cells of a given shape do what's called a T1 transition, which is the simplest rearrangement of neighbors in one of these things. And it's exactly true that this quantity governs the magnitude of the energy barrier for those transitions. That's what it governs. And cells regulate it by basically the magnitude of cortical tension, which is a measurement you can make with like a micro pipette aspiration device. And it's proportional, roughly, I have experts in the audience, but roughly proportional to sort of actin density and myosin density at the cortex of these cell types, of these epithelial cell types.
Thank you. Also, maybe a terminology question. What is an external processor exactly?
What is an external processor?
Yeah.
Here, I just mean anything that is not embedded in the system itself. So for that vibrating plate, they actually ran they ran the thing through a computer, an external processor, and the computer told them what to change about the object. It wasn't like it changed internally by itself. The computer changed things. It was an external processor. And by the glassblower, I mean, we all have a very good external processor in our brains. So it's the glassblower deciding where to pull the thing and the glassblower deciding where to heat it. But you could imagine that if the blob was able to heat itself in certain parts and pull itself in certain parts, then it could make a fish by itself. And that would be not external, is how I'm using that phrase. Yeah.
More questions?
So these models were all in 2 dimensions, right? Do you expect any of the conclusions to change for 3-dimensional?
That's a very good question. So we do have I didn't talk about it today, but we do have 3-dimensional vertex models. And also fiber network models. And they both undergo a rigid to floppy transition because it turns out, and that's kind of cool, it's a feature of them, I think, that unlike first order rigidity transitions, which absolutely depend on the dimensionality of the systems, second order rigidity transitions do not depend at all on the dimensionality of the system, only the geometry, because it doesn't change the connectivity to constraint ratio or degrees of freedom ratio. So they do behave in exactly the same way. They transition at a number, which is the dimensionless shape index of a 3D system, which is the surface area volume to the 2/3. And they seem to work really, those type of models are predictive for things like stratified epithelia, which make up your skin and stuff. So they are actually well validated now in tissues that are in 3 dimensions.
Okay, last question.
So in the cost function equation for like biological system, I thought it's the desired tissue versus like the actual tissue.
Yeah.
I was wondering, so like in biological systems, do they have a signal to like the cell, like say like the cells in a developing embryo? Like, do they have a signal that says like how close the thing is to the actual desired tissue?
Yeah, so let me rephrase. It's a really good question. Let me reframe your question, which is that I didn't say how this process stopped, right? Because the way that we did it is I said, oh, I'm just going to keep changing my target length to make it longer and longer. But biological systems are self-limiting. They stop changing their aspect ratio when they get to an aspect ratio of 2 and not 3. And I did not explain how that happened. And it's a very good open question. So like I didn't, like presumably there might be a learning process, or maybe you don't want to frame it that way. Something else that comes in and says, hey, stop doing that learning rule. Stop doing that. Do something else now. Yeah.
Thank you.